Hi everyone, welcome to a video in the motion series, this one focusing on difficult work questions. This will also be the first video in which we introduce the idea that gravity is doing some work on objects. But the first question involves no difficult ideas about gravity. It's just a snowmobile that is reaching a rough patch of snow and slows down considerably. So at this moment in time here, the snowmobile has initial velocity 25 meters per second and a mass of 200 kilograms, and that mass will not change. But as the snowmobile and the person encounters this rough snow, the snowmobile and the person slow down considerably to a final velocity of 5 meters per second. And that occurs over a distance, if this is where they start slowing down, of 30 meters. And the question we want to answer is, what was the force, or the average force, of the rough snow on the snowmobile acting in that direction there, which slowed it down. So moving this all over here will give us some room to work. Recognize that the work done by the rough snow on the snowmobile has slowed down the snowmobile. It's taken away from its kinetic energy. So let's find the initial kinetic energy. EK is equal to a half m, so that's 200, times v squared, so 25 squared. That comes to a total of 62,500 joules. And the kinetic energy here, the final kinetic energy, because we'll assume beyond this he's not slowed down anymore, is equal to a half m v squared, so 5 squared, which is equal to 2,500 joules. There's been a considerable change in the kinetic energy of the snowmobile and the person due to the work done by that friction force there. The total change, the change in kinetic energy, is equal to EKF, take the initial kinetic energy, which is 2,500, take away 62,500, which is just 60,000 joules. Well, actually negative 60,000 joules. But what this is telling us is that the work is being done in the opposite direction to the kinetic energy. So if that is the change in kinetic energy, the magnitude 60,000 must also be the work. So the work is equal to 60,000 joules, and we'll just say against the direction of motion. So the examiner knows, we understand it was negative work, but we're saying 60,000 against the direction of motion to the left. And that work must have been made up of the friction force acting over the distance in which it's slowing down. So 60,000 is equal to the average force times that distance was 30 meters. So 60,000 divided by 30 is 2,000 newtons. 2,000 newtons there. Moving on to our next question. It involves a pebble being dropped into mud. So the pebble, will show it just before it's dropped into mud. We got a white pebble. Here it reaches the surface of the mud, and then the mud is here, and it comes to a stop down here. So it moves through that mud there. Right before it impacts the mud, it has an initial velocity of 10 meters a second downwards. When it comes to a complete stop, it has a final velocity, of course, of 0. The rock, or pebble, we'll say has a mass of 0.05 kilograms or 50 grams. And what we want to find is the average force of the mud on, we'll call it the pebble, mud on the pebble, because that is what is actually bringing the pebble to a stop. So first of all, let's look at the amount of work, the net work that's been done on this pebble. It started off with a initial velocity of 10 meters a second, so its initial kinetic energy was equal to 1/2 mv squared, or 1/2 0.05 kilograms, using kilograms here, times 10 squared, so that's 0.05 times 100, or 2.5 joules. So this pebble has lost 2.5 joules worth of kinetic energy as it's come down here. The distance the pebble dropped in the water, I forgot to add. This distance here, we'll say is equal to 30 centimeters. So if this is the net work that's been done on that pebble, work is equal to 2.5 joules. That must have been done by the average force, net force on the pebble over the distance it's dropped, so 0.3 meters. So getting the average force by itself, average force is equal to 2.5 divided by 0.3. That is equal to 0.3, 8 1/3, so 8.33 newtons. That is the average net force that must have been applied to the pebble. But here's where things get complicated. We're looking for the average force of the mud on the pebble, and that does account for some of the force acting on the pebble. If we just put in a force diagram here, so the force of the mud on the pebble, so force mud, is in that direction. But don't forget there's also the gravity force acting on the pebble in that direction, which is equal to mg, which is equal to 0.05 times 10, or 0.5 newtons. So whilst the average force was 8.33 newtons in the upwards direction there, that average force was made up of the force of the mud and then taking away the force of gravity, 8.33. So really the force of the mud was 8.33 plus 0.5, which comes to 8.83 newtons worth of force. If you're finding the idea of gravity being taken into account with these questions difficult, there'll be more videos explaining this concept as we move into gravitational potential energy.